All right, so any questions before I get going? All right, I think we went through the problems in 2-7 section, 2-7.3 in the that Cooper book, right? All right, so now I want to, before I get into joint or conditional probability and then density functions where you have conditional probability based on two or more variables and stuff like this, what I'm going to do is I talked a little bit about conditional probability. I want to actually get into some of the probability distributions that are mentioned in section 2.6 in the book. I'm going to start with the most basic, which is power. You know, if you have, say, a current value, I, that's a random variable, it's Gaussian, then how is the powers distribution? What is that, okay? And this is in the older book, the one I'm referencing here, this one. It's Cooper and McGillam. It's chapter 6. And, pardon me, not chapter 6, section 6, 2-6. And we're going to do some of the problems, but I want to go through some of this stuff. I'm just going to mention these. And when you're talking about other distribution functions based on the Gaussian, you know, we talked about other distribution functions. We talked about the first distribution function was constant, right? Where the probability density function was constant over a range. You all remember that one? And from that, we got certain values and things like that. The second one was the exponential distribution. Do you all remember that? The time between any two events, the probability density function was an exponential variation. Now, if you take a look at the time between just one event and the next failure or success, and it's exponential, if you want the time between two of these, either failures or successes, however you want to put it, or three or n of them, then that was an Erlang. Do you all remember the Erlang class? Okay. Then we talked about, I didn't talk about the gamma distribution, but it was related to the Erlang, and I mentioned that. There's a lot of distributions. There's a chi-squared. There are so many probability density functions based on actual events that happen in the real world. And a couple of them that are very important to engineering besides Gaussian are the Rayleigh, and then there's the Maxwell, I call it the Maxwell-Boltzmann. They call it the Maxwell distribution. You know, you've heard of Maxwell-Boltzmann, right? Has to do with what? The velocity distribution of random variables in a gas. So, but before I do that, this is section 6. This is 2-6 in the book in Cooper and McLennan. So the first one is if you have power, and it's equal, usually it's P here, I squared R, and you talk about the actual distribution, this will make perfect sense to you. If you talk about the distribution of current here as a Gaussian random variable, that's 1 over the square root of 2 pi sigma, this would be sigma I, exp, normally it's minus I minus the mean value of I, squared over 2 sigma squared. Usually the mean value of I, and this would be sigma of I, usually the mean value of I is 0 for any AC signal. I think it makes sense, right? Usually you don't have an AC offset or a DC offset by an AC, signal with a DC offset, usually. So that's common. Now, if you think about this for a second, we're going to assume that the mean value is 0 here. And you look at this, and I'm going to try to sketch it out here. The density function would look like this if this is the current values, and this is Fi of I. I'm just showing you the density function, just trying to give you a visual, right? Now if you take a look at the probability that the power, and the symbol they use in the book, and I'm going to use is W, just because it's watts usually, that's the only reason they choose that. If you say between some value of A and B, what are you really saying? Well, here's the value, right? Now, power over R square root would be plus or minus is I. Do you all agree with this, class? I'm just showing you, if power is defined as I squared R in the simple sense, this would be I RMS power, and I would be the RMS value. You all with me on this, class? This would be the RMS envelope. But you could have 1 over the square root of 2 if it was peak power 2. You all follow me? If you talk about this, if you talk about the probability of power between A and B, what is that? That's the same thing as the probability that here the current, and I better do it this way. Since I gave power as A and B, then I would be equal to or greater than the square root, it would be minus the square root of B over R to the square root of minus square root of A over R. Now I'm saying this because there are negative values for current. So it'd be down here. This would be minus the square root of B over R. I'm assuming that B is greater than A. And here it would be minus the square root of A over R. It would be this area. But then you're also going to have an area where you're going to have the square root of A over R greater than or equal to I less than or equal to the square root of B over R. Now the reason is because current can be plus or minus and still render the same value for W, for the power. Do y'all follow me? If it's minus 1 squared, it's the same thing as plus 1 squared. Everybody with me on this? So then I'd come over here and I'd say it's also the probability of this being between the square root of A over R to the square root of B over R. Now take a look at that just for a second and let it sink in. Does everybody understand why I've drawn that picture and what it means? I'm just showing you how we can go ahead and get the probability density function for the power, for W. And then we could integrate that, but actually we don't have to. We can circumvent that if you just see the visual. Does everybody follow me on this? So do you all remember if it's got a mean of 0, the area under here is the same area as under there, right? You all with me? So this is really just twice the probability of this occurring. You all with me? So it's going to be 2 times the probability of, I'll just put 2 times the probability of square root of A over R less than or equal to I less than or equal to square root of B over R. In the book, he actually goes through and does the density function. I'm going to mention it, but I want to do these problems. I want to make sure you see the simplicity of this. If they ask for the power between any two values, it's really the same thing as the square root of the power divided by R between the values of current that are positive or minus, or if you just take the positive value, this is assuming a mean of 0, just take the positive side and multiply that by 2. You all with me, class? Now the density function he gets by this. I'm going to put him here, and then we're going to do a few problems, and you'll see the application. You'll see, hopefully, how obvious and simple it is. So for the probability density function, if you think about this, if we have f of I times d of I, now that's the probability density function of I times f of I, this is equal to the probability density function for omega d omega. That's the power, right? But there is one other thing that's mentioned in the book, and I have it in slides. I got a bunch more slides. You have to account for both roots. Do you all with me on this, class? So this would be right here. This would be for the positive root if you take a look, right? I mean, it could be positive or negative. But think about this. Remember, I said the probability of power being between A and B is this plus this. Do you all with me? So if it's actually equal to if there's a 0 mean, you can simply say it's going to be twice that. I hope you all follow me. Do you all agree with this, class? And again, just think of this as a differential slice. That, the probability density function, whatever this is, times di, the 2 accounts for both sides, would have to be equal to this. Everybody with me? So now let's go ahead and just try this and see if it works. So if I take f of W on that side, that's the probability density function for the power, I can say that's equal to 2 times f of I. And then, now if you look at this, this is di, that's dw, right? I have to take that downstairs, so it's times dw di. Can you all follow me on this? I'm just rearranging it. The derivative dw di is on the bottom. It's obvious if you just rearrange this. Can you all follow me? Can you see it back? Okay, guys. All right, what's that going to be? Well, here I have this. So when I do dw right here, di, I get 2ir. And that means down here, I can say this is equal to 2 times f of I. But now I itself, I'm just going to put in the simple sense, I is equal to w, or the power, over r square root. And we're only taking the positive root because I've accounted for the other part here. Normally I'd have to do both here. So it's going to be times the square root of, oh, I better do it this way, square root of w over r here, and divided by dw di. dw di is 2ir. I'm going to put I in terms of W, or power, so it's going to be equal to 2 R, and then I is square root of W over R. And you can see, you can go ahead and cancel the 2's, and you have f of I of square root of W over R. And downstairs, it's going to be really square root of WR here. Now, does everybody follow me? I'm just trying to track this. Okay, everyone? Now, you put in the value for the density function. Here it is. And I said it was 0 mean, so it's this density function right here. And you can see what happens. And you'll see this. You don't need to know all this to do the problems. But in the book, he shows you this in case you need to write a program for power density. And if you have a mean that's not 0 right here, then you have to do the individual values. Because if it's shifted, the area here will be different here if the mean's not 0. You all with me, class? So just be aware of that in case. So over here, what you're going to end up getting is the actual f of omega is equal to, and here it's going to be 1 over square root of 2 pi sigma I, and then it's going to be times exp to the minus, instead of I is equal to the square root of omega over, or of W over R, but it's squared, so it's just equal to omega over R, right? And it's really 2R sigma I squared. What I've done there, the 2 sigma I squares, because I is the square root of, like I said, omega, of W over R. When you square it, you get W by itself over R. So it's that, and then you've got to divide all this by square root of omega R. And I got a comment about this. Let me do it this way. All right, so that's the density function that would be for power. Take a look at this for a second. I want to show you an oddity. Now remember, this is assuming 0 mean. This is a really important thing just to observe. Now, numerically, you need to know this. What's the value of that density function at power is 0? Just look, evaluate. What is e to the minus 0? Anyone? What is 1 over the square root of 0? Same thing as 1 over 0 is, just say it, infinite, right, guys? You all with me on that? There's no wrong answers. Are you willing? If it's infinite, boy, that bothers me. The most probable value would be 0 for an AC current, all right? It would be. You give me this? Assuming the thing's symmetric AC, not like it's up most of the time, then down just a little up. If it's a standard sine wave, this density function, Gaussian density function does work, can work, pardon me. And that would be the most probable value. But if you're writing a numeric code, the only way to do that type of part of the integral, because it's going to infinity, would be using L'Hopital's rule, all right? And you would have to do that times something, because the problem is at 0, it goes to infinity. That's the only thing I want to make you aware of, and this is in the book. I'll tell you where it is. This is the first one. It makes sense. We're electrical and computer engineers. That would be the first density function. This is on page 77, 78, and 79 of the old book. So we might as well we can do the exercise 2-1 in the book. Can you just give me that? And this is in the older book. But let me erase this. I didn't put this down, but the mean and the standard deviation is easily gotten to. And you can get it from the current statistics. So, hold on. Let's do it over here. So what is this one?
Okay, so this is exercise 2-6.1. A Gaussian random voltage having a mean value of 0.
Oh, thank God. All right, so V mean equals, by the way, it doesn't matter if it's voltage or current. You know, for voltage, it would be what? Voltage in terms of power. Power would be V squared over R. For current, it would be simply I squared R. Follow me? In the simple sense. Go ahead.
And it has a standard deviation of 4 volts.
So I mean, sigma V squared is 16. Go ahead.
And then apply to a resistance of 2 ohms.
2 ohms?
2 ohms.
So we got this. Here's my V, and you got R equal 2 ohms. Go ahead. I haven't done this one.
And then part A is to approximate probability that the power dissipated in the resistance is between 9.9 watts and 10.1 watts.
So they want the probability 9.9 greater than omega, less than 10.1 watts, right?
Yes.
Should be inside the parentheses. All right, think about that for a second. We got a voltage here. Power is equal to V squared over R is equal to, if you look at this, when I think about V, it's going to be equal to R omega square root, of RW. So V is equal to the square root of RW, right? But it could have plus or minus values. Do you all agree with this, class? Now, I'm drawing this up here because I think it'll help you. It'll help in general. What do they want the probability of between a couple of values? So if I go ahead and put the density function for the voltage, which is the same for the current, the density function for the voltage here, since it's got a 0 mean, it looks like this. And the f of v here would be equal to 1 over square root of 2 pi sigma v exp to the minus v squared over 2 sigma squared of v, right? That's the density function. For the power to be between there and there, that means what? Here, the voltage would be equal to the square root of the power R plus or minus that value. That means V has to be between here. It's the same thing as the probability of the voltage being greater than, we'll go to this one. So it's going to be greater than minus the square root of power times 10.10. Let me do it this way. Matter of fact, I'll do it right like this. I'll talk about the power of 9.9 greater than the power less than 10.1 is the same as the probability of the voltage being, it's really, let's just do it this way. 2 times the probability, we'll take the positive one, of the square root of 9.9 times the resistance, which is 2, 9.9, and this is going to be times 2, greater than V, less than square root of 10.1 times 2. Wait a second. Yeah, times 2. Y'all agree with this? How do you do that? What's the easiest way? What if we just want the probability, forget that 2, of this? You could use characteristic function, or you could use the Q function, right? Either one will do this. Do you agree with this? So let's get, y'all know what I'm talking about here? If we use the table's characteristic function, you have this in your calculators, right? And you have it in yours, right? So what is it going to be? We'll do it here. Forget the, no, we'll put the 2 down here. So that probability, the probability of 9.9 greater than W less than 10.1 is going to be 2 times, and here we're going to take the characteristic function that the voltage is less than this. Do you all agree with this? Now, I don't know what that is, but it's going to be really the characteristic function of the square root of 10.1 times 2. If you have your calculators, you can do this. Whatever that is, and it's going to be minus the characteristic function of the square root of 9.9 times 2. It's twice that, so what is that? You all know what the characteristic function is, right? Characteristic and Q are related. Characteristic plus Q function is equal to 1, right? And I'll put it here. What is the characteristic function? Actually, you know what I should do? Take it back. The cumulative distribution. I didn't normalize it. So this is going to be F right here of I minus F of I. I didn't normalize this. I'm sorry. So to get the characteristic function, right? Normally, if you talk about F of I of any value of x, that's really what? The characteristic function itself. And then you have to do what? You have to take x minus the mean of x over the standard deviation of x. Do you all remember that, class? So our mean is 0. So it's really, I have to divide that argument in there. If I want to replace this by the characteristic function, I have to divide this by the standard deviation. Do you all agree with this, class? Y'all follow me on this? Okay, we'll do it right down here. This is going to be 2 times, and it's going to be the characteristic function. You can look in tables, or you can do this in your calculator. And it's going to be the square root of 10.1 times 2 over the standard deviation, which is 4, right? Minus the characteristic function of the square root of 9.9 times 2 over 4. That's 4 outside. And what is that value? If your calculators allow you to put in the mean and standard deviation to get this cumulative distribution, you can go straight for it. You don't need the characteristic function. But
It's 0.0047.
did you use your
I
calculator?
use the cumulative distribution function.
All right, 0.0047.
Yes.
What's the answer?
0.0048.
477, so that's wrong.
Y'all with me on this? It's within the margin of error. Okay, what's the next one?
The part B is the probability that the power dissipated in the resistor is greater than 25 watts.
You guys tell me how to do that one.
So it'd be 1 minus the cumulative distribution function at 25.
Yeah, but we have to multiply by 2. Remember, if you think about that curve here, if it's greater than 25, there's going to be a point down here, minus A, and a point here, plus A. It's this area plus this area, so it's twice that area. You all with me? So everybody follow me on this one? So what would it be? The probability that the power is greater than 25 watts, right, is the same thing as the probability of the current I being less than, what is that? So what, omega here is equal to V squared over R. So V is equal to the square root of omega R, and it'll be minus this plus that. Omega is 25 times R is 2 square root. So its probability this would be minus the square root of 50. This would be plus the square root of 50, right? So you can use a Q function for this. Q is just the probability it's greater than that. Or you can use characteristic. It doesn't matter. So for this one, I'm going to go ahead and just do it. It's going to be twice. And It would be the cumulative density function, it would be actually 1 minus the cumulative density function of I being greater than square root of 50, square root of 50 here, or it would be 2 times 1 minus, and then the characteristic function, if you wanted to do it, the characteristic function, it would be that minus the mean, which is 0 over the standard deviation, 50 over the standard deviation is 4, right? Yeah. So you can get it this way. What do you get for that? You can look at the tables. If somebody wants to do it with tables, just tell me if you get the same answer. You don't have to. You can use your calculator. What'd you get? Anybody?
I'm not getting the right answer.
Well, I mean, do you all agree that this is right, first of all? This right here, 1 minus this is the area above. You got to double it, right? So do you have a characteristic function?
I didn't get the last one correct. So.
Maybe it's wrong in a book. Okay, you got my book. I can do it right here. I want to make sure it's right. This shouldn't be too hard, but anymore, I'm not going to say too much until I do it.
I get 0.077.
What's the answer?
0.077.
No, the answer is 0.7364.
0.7364? I don't know.
That's what the answer is, but I'm also getting 0.077.
Let's see if it's right, because I'm going to level with you. Books make mistakes.
So for his answer for part C, it's 0.077.
He doesn't, those aren't in order.
Oh, well then, yeah, it's 0.077.
Does he have 0.06? They're not in order, the answers.
Okay.
So 0.07 sounds right. What's the next part?
The probability that the power dissipated in the resistor is less than or equal to 10 watts.
How do you get that? Get a mental picture before you do it. I'm going to go to this thing. I'm going to tell you, if you think, just draw it out, it'll save you. I promise you it'll save you. So here, I'm going to recreate this density function. Now this is for current. You don't need to draw the density function for that power. You really don't. So here we have current. Here's the density function. The sigma I is equal to 4. The mean of I is 0. Right? So here's the density function. Now, less than what?
Less than or equal to 10.
Well, I mean, that's power, right?
Power dissipated is less than or equal to 10 watts.
So if power is 10, that's equal to V squared over R. So it's 10 times R, which is 2, right? Square root. So the only thing you do is go down here. That's going to be square root of, minus the square root of a 20, right? This is plus the square root of 20. And this is the area we're talking about in terms of current. Can everybody follow the reasoning behind this? Everybody? You with me? Now, you can do the integration of that, but that doesn't have a closed form table. Mathematically, you can do it on your calculators. I'm sure you can. But it's much easier to just think about current. Because you got that density function, you know the integrations of it. You all with me? You've got tables. Now, what's this going to be? Isn't it really twice the probability it's greater than 0, less than 20? Correct, class? So that would be what? Technically, it would be this probability of greater than 25 watts of the wattage being greater than 25 is the same thing or twice the thing of the probability of V being greater than, magnitude of V greater than twice just V being greater than or equal to 0, less than or equal to the square root of 20. So you can do this with characteristic function, or if you have the ability to just put in the cumulative distribution with the mean and variance, and I think yours does that, right? How many have that ability on yours? Do you guys, if you have it, please make use of it. It's a lot easier than tables, and it's right in front of you. Get used to your calculus. So this is going to be 2, right? And then its probability of, since it's cumulative, 20, so it's going to be, in terms of characteristic function, it's going to be square root of 20 over 4 minus the characteristic, by the way, what is the characteristic function of 0? What is the integration from minus infinity to 0 of a Gaussian distribution with 0 mean? It's 1/2, isn't it? It's 1/2, minus 1/2. So what is this? Anybody? Did you get it?
0.368.
Anybody?
So the answer is 0.736. I think you should have multiplied that by 2.
Yeah, that's what.
It's got to be
Yeah.
2 times that. So,
I just
Did you get that?
Yeah, it's 0 to 26.
but you got to multiply by 2. Y'all with me? Right answer. All right. Now that's a good it's a good problem because we're electrical and computer engineers, and frankly, I've not run into this particular problem related to power distribution or anything, but I could see something in Halpin's class or one of these guys that teach it, something like this coming up. In radar, a lot of times we get what's called, it's called the video, it's really the magnitude of the voltage. That's where I'm going next. I don't get this particular type of problem with radar. I mean, not that distribution, but I could see how it happens. What I'm about to show you, and we'll do the problems in the back, is the next distribution is the Rayleigh distribution. I want to tell you this is very important. So this is the one you really kind of focus on. You'll see the reason for it. It has a lot to do with things that are related to both radar, engineering in general, and frankly, if anybody works for the military and they talk about targeting things with weapons, then this distribution is what they use all the time. I mean, you'll see it all the time, and I'll tell you how it comes about. Has anybody here heard of the Rayleigh distribution? Now, this one's kind of interesting because the distribution function we got for the power had only strict positive values. Power cannot be negative. You all follow me? It goes, real power goes from 0 to some value, positive value. Current can be plus and minus because it has a directional sense. Power doesn't. So we talk about the next one, which is Rayleigh, and I use this one all the time. In radar, here's what happens. If you have something, and now we're going to get an orthogonal coordinate system. If this is x and this is y, and we know the probability density functions for both of these. We're going to assume they have a 0 mean, almost always they do. This is considered the bullseye of the target. I'm just going to try to give you a visual on this. So in general, they talk about a radius vector r. They could care less about the angular measurement. They only care about how far from the bullseye you are. Has anybody ever shot rifles or anything, BB guns, bone arrows? You'll know that the only measurement in the Olympics or any other things, pistol shooting, long range, PRS matches and all that, is the missed distance from the center of the bullseye. They could care less if it's below, above, whatever. They just want to know the distance, r. And this would be at a point x, y. Well, first of all, that magnitude of r is simply square root of x squared plus y squared. Now, this also pertains to things that are orthogonal. You know, when they talk about things that are orthogonal, in spatial coordinates, they're at right angles. X and y are at right angles. That's all it means. If you dot product any x vector, it has 0 y component and the same the other way. When you talk about orthogonal behavior in signals processing, it means that the integration of any two signals, say x1 and x2, over a period, if they're orthogonal, is 0. That's all it means there. There are many other things that are, quote, orthogonal. All right, and I'm not going to get there. I'm just going to show you this distribution, and you'll see the application as we go through here. So first I want to do this because it has to do with targeting. You can imagine that. All right, if f of x and is the same thing as f of y, in general, this is true for targeting, and it's equal to a distribution of 1 over the square root of 2 pi sigma x or y, it doesn't matter, exp, right here. We're going to assume both have 0 mean. We can account for a non-zero mean, but it doesn't usually appear, of minus x squared over 2 sigma x squared. And by the way, if they have this, if f of x and f of y had 0 means, but they had different sigmas, we can account for that too. What I want to do is make it simple at first. Y'all with me? So the density function for x and y are the same. And if you think about this logically, if somehow you could get a visual of this, if I could actually draw this density map out of the board, you would see a peak here. But really what I'm saying is if this is x-axis, here's the density function, and this is the y-axis, then the density function would look like this, if you think about going. And if you multiply the two together, you kind of can see it. But here's what the density for f of r would become, all right? Now, usually the way they do this, and I'm going to say there's two roots to this one. Normally, and you don't need to remember this, if we wanted the density function for r, f of r of small r, what we'd have to do is find the density function for f of x. If you think about this, f of r dr here is going to be f of x dx, right, plus f of y dy, f of y, pardon me. Since dy is dx, it would be twice that. And then you would have to do something where you would have, since this is dr here, you would have 1 over dr, might as well go dx, and then you would have twice times f of, call it f of x, and you would have to, remember how we did this before? You got r is equal to the square root of that, take the derivative, you get 1/2 times x squared plus y squared to the minus 1/2 power, and you can do all this. You don't, it's unnecessary. Lord Rayleigh proved this, but I'm just telling you that's how the proof comes about. You understand how you would get there if you wanted, right? I did this for the other one, right? For the power. You can do it the same thing here. Here's what it comes down to. When you talk about, and write this down, f of r, this is the Rayleigh distribution, is really going to be equal to r over sigma squared, and this is going to be sigma of x or y. This is important. This is the standard deviation. Actually, in the book, I want to make sure you got my book, but hold on for 1 second. Can you find the Rayleigh distribution? It's the next section.
Yes.
Just tell me what page it's on.
It's on page 80.
Okay. And then it's going to be exp, and it's going to be to the minus r squared over 2 sigma x squared. Now, it's important to note that these are the standard deviations for the Gaussian distributions that are expressed in terms of the f of x and f of y distributions. Y'all with me? They're usually the same, and in the book, does he have that there? He'll have sigma, and it'll be related to either x or y.
It just says sigma.
All right, the standard, write it down. The standard deviations are the standard deviations for x or y that are Gaussian. It's the Gaussian standard deviation. That is the Rayleigh distribution. It has a Rayleigh standard deviation as well. They're different. Y'all with me? Now, what does this look like? Well, it's strict positive, and here's what it actually looks like. But this is a nice one. And you'll see why in 1 second. If you take a look at this, if this is r, and you take a look at this as f of r, as a distribution, at 0, it's 0. Y'all see that? When r equals 0, it's 0. Unlike the power. Remember with power it was infinite? This gets 0. And then it'll come out here, have a peak value, come down like this. Now, y'all with me on this class? Y'all with me? All right, now, that's the Rayleigh distribution in a nutshell. It has a mean value, and we could prove that. If I wanted the mean of this, I'd have to multiply this by r. I'd get an r squared, right? Then I'd integrate it from 0 to infinity. Y'all follow me on this class? To get the expected value? I'm just going to write it down. The expected value, or the mean value, and this is for Rayleigh. The mean value is the expected value of r, and that's equal to the square root of, and his book is going to have pi over 2 times sigma x, and this is the Gaussian random variable. Now, he'll have that. I'm not sure where he has it in the book, but
It's still on page 80.
all right, this is on page 80. We could do it. You got to put multiply this by r, and you have to do the integration. Do y'all follow me on this class? It's an integration by parts once, but I'm not going to mess with it right now. Then he's going to say that's the mean value, and I'll just put, he'll put r bar is equal to the square root of pi over 2 times sigma x. And I'm putting sigma x for a reason. I want to make sure you know it's Gaussian. Then he's going to say that r squared bar right there, and that means you multiply this by r squared, so it's r cubed and integrated. For that one, he's going to give it, it's just, and this is important, this is nice. And you'll see why in a second. This is just simply twice sigma x squared. What page is that still on page 8?
It's on 81 now.
All right. So this is the mean squared value. This is on page 81. And finally, if you got the mean value and mean squared value, now remember, this is for r. That's the Rayleigh, right? You'll notice this is 2 right here. Twice the actual mean squared of x or y. It makes sense. You'll see why when we do Maxwell. Maxwell will be 3. Now, if I wanted to get the actual variance, now this is for the Rayleigh. How do you always get the second moment, class? Come on, man. Don't treat me like I'm a foreigner. Does anybody remember? What's the second moment? I mean, sorry, the second central moment. It's always this minus this squared, right? It's always going to be r squared bar minus r bar squared, right? It's always the second moment minus the mean squared for the second central moment. That's always the truth. Doesn't matter. So what's this going to be? Sigma of r squared is equal to that squared is 4, right? 4 sigma x squared minus that squared is pi over 2 sigma x squared. And I mean, you can do the math on this one. So it's really going to be what? 4 minus pi over 2. This I can't do in my head. Sigma x squared. It's like 0.439 or 429. What is it? 429 times sigma x squared. And that is the actual variance. Standard deviation, square root of that. You all with me, class? But that is for the Rayleigh distribution for that distribution. Now the best thing to do, now we talked about it, is just do some problems. I'm going to do the exercise first. I don't know where the exercise is in here. There. Give me 1 second to erase. I think this is the best way to learn this stuff. Just show you examples after theories is shown. And you'll see this is not tough. Now, I'm going to level with you. With this stuff, you're going to have to do problems. You're going to have to do problems, and I'll give you as many as you want. I can give some out of other books too. But that's the only way to really get a feel for this. It's sort of like with those, when you had the binomial distributions and stuff, and you got all that stuff with, remember the Cabaret, the Merlot, and the, what was the other one? Zinfandel problems. You had to do the problems to get familiar with what could occur, and it's really just, it's called the counting sequences possible. And you can do things with, you remember there was permutations and then just combinations. So, now for this problem. This is exercise, which one?
No, it's 2-6.2.
Go ahead.
And it says an amateur marksman shooting at a target 10 inches in diameter has an average miss distance.
Here's one tip to you. Draw the picture and put the values, because you're going to think radius a lot of times, not diameter. So the diameter, D, is 10 inches. That means the radius here, R, is 5 inches. Be sure you remember that. Go ahead.
And it has an average miss distance from the center of 2 inches.
So now he's saying this is R bar is 2 inches. Has nothing to do with sigma x or sigma or x bar. You all with me on this, class? Go ahead.
And then the question is, what is the probability that he will miss the target completely?
All right, now he wants the probability, pardon me, given this information, right? He wants the probability that really the value of R is going to be greater than 5 inches. You all with me? Not. And by the way, I didn't do this, but I need to do it now. Before we do this problem, you're going to see that this is the nice reason I really like this. You don't need tables or anything with Rayleigh. So don't write it down, just watch this. I want to do it here. Remember, the density function for the Rayleigh distribution is equal to R over sigma x squared exp, or sigma that has to do with the Gaussian, over r minus r squared over 2 sigma x squared, or sigma squared, right? Now, just work with me here. If I take a look at this distribution, it looks like this. Try to get a visual on that. The mean value is what? Square root of pi over 2 sigma x, right? Y'all with me, class? That's not important. Well, it is and it isn't, but just listen to me. Now, if they want the probability of anything here, we want the probability from anything we want from one point to another point. There are no negative values for that, all right? It's only positive, right? So we got to integrate that, right? Just keep watching. So if I take a look, and I'm just going to put the probability, if it's a Rayleigh distribution, of R being greater than A, less than B, or better yet, let's go the probability from 0 to B. Let's start this way. So this would be like the cumulative distribution function. Remember before we started minus infinity? Here we started 0, okay? This would be like the cumulative distribution function. Well, that would be the integral from 0 to B of this, which would be of R over sigma, I'm going to leave it a sigma here, exp to the minus R squared over 2 sigma squared, dr. Do you all agree with that? Sorry, my R's look a little like V's, but you all with me, class? All right, the way to do this one is nice, because if you just let U equal to exp to the minus R squared over 2 sigma squared, take a look at this. What is du equal to? Well, it's going to start off by being e to the minus R squared over 2 sigma squared, right? Then you have to take a derivative of that. The derivative of that is what? Minus 2R, right? Over 2 sigma squared. Or it's really one. It's equal to minus R over sigma squared times e to the minus R squared over 2 sigma squared. Do you all agree with this, class? Now, what do we have here? Isn't this really the integral from 0 to b, right here, of minus du? Take a look. Do you agree with that? I want to make sure. Does everybody agree? I know it's a Monday morning. You got to kind of kick yourself, force yourself to think. Follow me on this? How many do? You're still suspicious.
I got lost.
Well,
Like how the R over sigma squared disappeared.
the what?
So you have minus R over sigma squared there, but that's du.
This is 2 over 2 cancel, right?
I see where it comes from in that, but just over here in the integration. 'Cause
What?
On the right side right there, because you already had an R over sigma squared. But then,
Yeah, but that, what is that? That's this, isn't it?
Okay, I see now.
But you have to put a minus sign because it's this is du, right? But you got to put a minus over here, make it minus, make that plus. So okay, because you got to get rid of that minus. Now, what does that really mean? Can't I just switch the limits and go from b to 0? You agree with that? All right, now evaluate. That's u evaluated at 0. What is u evaluated at 0, class? When r is 0? Y'all see it's 1. E to the 0 is 1, so it's going to be, this is nice. It's simply 1 minus what? exp to the minus, whatever this is, the limit, b squared over 2 sigma squared. That's all it is. 1 minus the exponential is the probability that it's between 0 and that point. You all with me? How many see this? I like this distribution because there's no tables.
Yeah.
It doesn't, now, getting back to this problem, he gives us the mean, he says the average is 2 inches, right? All right, now, that 2 inches has nothing to do, well, it does have something. It's not X or Y's mean. That is R's mean. And that means the actual value of R mean is equal to the square root of pi over 2, right? times sigma. Yeah. So we can get sigma. Y'all follow me? And this would be sigma of x or y. So I can say sigma itself is equal to 2 times square root of 2 over pi. And can you give me that? Anyone? I just want to put it down. It's not hard right here, if you see this part. It may be boring, but it's not hard. You got to focus, though. Anybody?
Got 1.595.
Anybody confirm? I think that's right. 1.595 inches, right? So now, if we want the probability of r being greater than or equal to 5 inches, that's to miss the target, right? What is it going to be? Wouldn't it be 1 minus the probability it's less than 5? How many see this?
1 minus.
Yeah, we're going to put it down, but it would be, see this right here is the probability it's between 0 and b. If we want the probability it's greater than b, it would be 1 minus this. Can you all see it's just the exponential there? How many can? I'll write it down for you, so it's going to be, this is equal to 1 minus quantity, 1 minus exp to the minus, and this is going to be 5 squared, right? Because it's r squared over 2. And then sigma squared, what was sigma? Is going to be this squared, right? And so that's going to be 4 times 2 is 8 over pi. So it's going to be 8 over pi downstairs. You don't have to do it this way. What it really amounts to is the ones cancel, and you get exp to the minus, and it's going to be 5 squared is 25 over 8 times 2 is 16, and then pi is upstairs. So can you tell me what that is, people? Anyone? Minus 25 pi, not much of a pi, but it should be this, minus 25 pi over 16. I don't know. Anybody? Can you all follow me how I got that? What did you say? Can't be negative. Oh. Yeah, now take the exponential. I'm sorry. I want to know what the whole answer is. You're right. I'm so sorry. 0.00738. Is that jive with one of those answers?
Yes.
Y'all with me? What's the next part?
That was the only question.
That's it? What? That's exercise what?
Exercise 2-6.6.
Is there another exercise right after that?
No, it goes into Maxwell distribution.
Tell you what, before we do Maxwell, go to section 2.6 out there. Hold on. I want to do another one on these because you got to see how easy it is. Okay, we'll do this. It says a current having a Rayleigh distribution. This is 2-6.3. I haven't done this one. I haven't done a lot of these, but this is stuff I'm fairly familiar with. I do use it. We'll get into Maxwell. Yeah. But I need to do these problems so you can see this. Go ahead. 2-6.3, right?
Yes.
Old text. Go ahead.
So you have a current having a Rayleigh probability density function.
So, all right, this is Rayleigh, so that means Fi of I. Unlike the last one is Rayleigh, which means it's going to be the current or I here. Tell you what, we're going to use R so it'll stick with it. Just say R is equal to I in this case. And it's going to be equal to R, that's Rayleigh, over sigma squared. Now that's got to be the sigma of the Gaussian, though. Just remember that one thing. It says it has a Rayleigh distribution, all right?
Yes.
exp of minus r over 2 sigma squared. Now these are Gaussian. I'm going to put x there so you remember. Go ahead. As a mean of what?
It has a mean value of current is 2 amps,
Go ahead.
and it's passing through a resistor with a resistance of 2 pi ohms.
All right. So here's the current. It's strictly in one direction. It is a varying DC current, if you think about it. Current's going that way. So, and that's the I right here. And you got R is 2 pi ohms.
Yes.
Okay, that's an odd value, but go ahead.
Okay, and the first part of the question is, Find the mean value of the power dissipated in the resistor.
All right, I'm going to do something at this point. Here he says this is the Rayleigh distribution's mean, right? I'm just going to try. That mean, I'm just going to leave it as 2, is equal to the square root of pi over 2 times sigma, which would be the Gaussian's associated distribution, right? I don't know what it came. Y'all with me on this, class? We're going to need this value. So that means sigma for this one is equal to what?
Should be the same as last one.
2 times square, that's right, 2 times square root of 2 over pi, okay? Now, that's important. Next, when we look at this, just by itself, we've got that value, right? For the current itself, which is a Rayleigh distribution, the squared value here, right, of the current would be equal to 2 times sigma squared. You all follow me? That's the sigma of x we just calculated. It would be related to the Gaussians that this Rayleigh came from. Are you with me on this? Some of this stuff seems a little odd. I'll give you it, but you got to follow me on this. So that's going to be 2 times that value squared, which is going to be 2 times 4 times 2 over pi. 2 times 2 is 4 times 4, which is 16 over pi, is r squared. And while I'm at it, the value sigma r squared, this is the variance, or the second central moment, is going to be 0.429 times the value of sigma a Gaussian squared, and that's going to be 0.429. You can write this any way you want, times this, which is 16 over pi, and get that all down. I'm just putting these up there because we may need them, we may not, but I want to make sure I repeat them enough so it stays with you. Y'all follow me? We got the mean, we got the second moment, and we've got the variance for this, if you want it. So now read that part of the problem. He wants the probability of what?
He wants find the mean value of the power dissipated in the resistor.
Okay, so first you got to write down power. Oh, mean value of power. So this is Rayleigh. It's strict positive. This is the beautiful thing. Just think about this. Power, if the current is Rayleigh, it's all positive I, right? With me? So what is power? It's I squared R, right? Now take a look at this. What is the expected value or the mean value of the power? That would be the expected value of I squared of R, right? Think about this for a second. R is a constant, so it's the expected value of I squared. What is the expected value of I squared?
2 sigma squared.
Isn't this equal to it? Isn't that the expected value of R squared equal to this, right? I'm just trying to underscore the point I'm making, right? 2 times this, right? Or it's equal to 16 over pi. So that's R times 16 over pi. And R is 2 pi. Strange that he chose 2 pi. So it's 2 pi times 16 over pi. Or it's going to be what? 2 times 16 is 32 watts. Is that the right answer? Can you check, anyone? I haven't done this one. I'm pretty sure it is.
So you have answers in the back.
No, I posted the answers to this. Do you remember seeing the answers? They're posted on the homework, I think. What is it? 32 is right? Okay. Y'all with me? What's the next part of that problem? Thank you.
Find the probability that the dissipated power is less than or equal to 12 watts.
Okay, how are you going to do that? You can do it a couple ways. How are you going to do it? What's the probability the power is less than or equal to 12 watts? I'm going to put it here. Think about it, guys. How do you do this? What's the probability of omega less than or equal to 12? Power less than or equal to, come on, guys. What's this? Well, I, since I is strictly positive, means what? I, W, or power over R, right? Right? If this is less than or equal to 12, the power, if we put 12 over R, right?
Wouldn't this be the upper level for current? This would be the current less than or equal to what? Square root of 12 over 2 pi. And that's equal to what? Square root of 6 over pi. So it would be what? Isn't this the same thing as the probability of R? I'm going to use R instead of current because R equals I in this one. Is less than or equal to square root of 6, right? Over pi. And what is that? I know I just gave you this, but remember, it's a cumulative density function, right? From 0 to that point. So it would be, anybody at all. Give you a hint. 1 minus exp to what? Minus r squared over 2 sigma squared, right? And remember, that sigma is the sigma associated with the Gaussian point that he didn't even talk about. But it's this sigma. Got that, everyone? You've got to calculate that first to do these problems correctly. So it's going to be this value squared, so it's 6 over pi. There'll be a minus sign there because that is squared over 2 sigma squared. What's sigma again? That's going to be what? 4 times 2, 8 over pi, isn't it, class? So it's going to be divided by 8 over pi. And what is that? That's 1 minus, I'll get out of your way in a second, exp right here to the minus, let's see, minus 6 over 16. And the pi's cancel, don't they, class? Sure. So what is that? Minus 3 over 8, whatever that is. So it's 1 minus exp to the minus 3/8. Can you tell me what that is? Anyone? Do y'all agree with me here? How many see this? It may bore you, but you see it over there? I'm just saying that this is, remember, that's the cumulative density function will be 1 minus e to the minus r squared over 2 sigma squared. The sigma is the sigma related to the Gaussian, and that's the only thing you have to keep straight in your mind. Because you can easily grab the sigma related to Rayleigh, which is wrong here. You got me? All right, what is, anybody? 0.3127. That's 1 minus that? All right, is that the answer? It is? Okay, good. What's the next part?
The next part is to find the probability that the dissipated power is greater than 72 watts.
Guys, can somebody do this for me? How do I find the probability that the dissipated power, remember this is current, this F of R here of R is related to current I. How do we calculate the probability that the power is greater than 72?
72.
We're really
72
talking
watts.
about an area out here where instead of power, we're looking at current. You all agree with this? Current greater than what? Well, if power is equal to, that's I squared R, right? So W over R square root is current, right? So the probability of current greater than 72, 72 divided by R would be the probability of what? The probability of I being greater than or equal to, think about it, 72 over 2 pi is 36 over pi square root, so it's square root of 36 over pi, right? And that's 1 minus, greater than 72 is 1 minus the quantity, 1 minus exp to the minus that squared, which is minus 36 over pi over 2 sigma squared, and sigma is 2 square root of 2 over pi, so it's 4 times 2 is 8 over pi. So this is going to be 8 over pi. He chose that for a reason, right? Because that's just simply exp to the minus, and it's going to be 36, so it's 36 over 16. Can anybody tell me what that is, people? Anyone?
0.1054.
1054. Is that the answer? I mean, did you do it in your calculator, though? Can you confirm that? I just want to make sure. Got it? Y'all with me on this? Okay. I'm going to try to get through some of the Maxwell-Boltzmann. This is a good problem. Rayleigh is very important. Now, Maxwell is very important, too, because when some of you, especially when you get into your senior level and probably your graduate level courses for some of you, Maxwell-Boltzmann distribution, the Maxwell he calls it, is really critical because that is the velocity distribution of molecules in a gas and many in a plasma too, and it is something you should be fairly familiar with for a lot of reasons. When I did my master's work was within plasma stuff. It was reactive ion etching related to solid state signal processing or solid state materials processing, but the distribution of the neutrals in a gas, the velocity distribution, is always going to follow the Maxwell distribution. Let me explain this. So when we talk about Maxwell, I'm going to put Boltzmann on here too because it's really... Have you all heard of the Maxwell-Boltzmann distribution or Maxwell class? I mean, this is like super classical. It's both in physics, in chemistry, in engineering. It's used everywhere. In general, if you have velocity distributions in a gas, if you take a look at one component, say xv of x, they will be Gaussian. All right, now sometimes if there's an electric field and you look at ions, which are ionized, then this will skew over here. But over the central part, over the mean value, it's Gaussian. That's both for the velocity, x, y, and z direction. So if you talk about the magnitude of the actual velocity, he just calls it v. That's the square root of vx plus vy plus vz squared. That's it. Now, if you think about this, remember before the radius vector was the only thing important for the target stuff I talked about? How far you miss? Here, this is really a spherical surface, if you think about that. If you think about a spherical surface, and you wanted the actual probability of the velocity was between v and delta v, what you're really thinking about is a probability density function where the surface of a sphere is 4 pi r squared, right, or 4 pi v squared times dv. That would be the volumetric idea you'd have in your mind of the probability we're calculating. So I don't even have time to do it all, but if you take a look at f, and I'll just call it f of v. This is going to be for the Maxwell-Boltzmann distribution without going into the proof. In his book, what page is that on?
It's on 82.
There's some neat things that come out of his. I got that down. This is going to be the square root of 2 over pi. And then you're going to have not a single power, but this is going to be v squared here over sigma squared, or sigma cubed, pardon me. And write this down. This sigma here is the Gaussian sigma. So it has to do with this. Sigma related to that density function for either x, y, or z velocities. You all with me on this? Please make sure you know this. Those sigma values there for both Rayleigh and Maxwell have to do with the Gaussian distributions they're derived from. Then you're going to get the standard EXP of minus, and in his book, he just does it the standard way. So this is going to be just, and it will always be for the exponentials, v squared over 2 sigma squared. But again, this is the Gaussian sigma. Now, I better put this down. Here's a neat part. There's 2 things we generally need, the mean and we need the second moment. So the mean, or actually the second central moment, if you take a look at the expected value of v squared, that would be like the second moment. It would be in general written as v squared bar. That's equal to simply 3 times sigma, and that's the Gaussian sigma squared. Do you remember how the Rayleigh was 2 sigma squared? Y'all remember that? Remember for the Rayleigh, the actual the second moment was just 2 sigma squared. Y'all remember that? And the third, so for Maxwell-Boltzmann, now we have 3 dimensions. It's just 3 sigma x squared. But there would be sigma associated with the Gaussians. Now the mean value of this, the expected value of just V, is equal to the expected value here. And that actually it's got a little different form. He has it as, he likes to do it square root of 8 over pi here times sigma of x. And I want to tell you, a lot of times in books, remember how I put down 0.429 times sigma squared for the Rayleigh's mean? All right. A lot of times they'll do it in terms of that instead of putting in terms of square root of 8 over pi or something. All right? I don't know why. They choose these things. They decide to. But this is the mean value. That's the actual second moment. And what page is that on, by the way?
This is on 83 now.
So out of curiosity, what would the actual variance be related to the voltage, the magnitude of the voltage? It's always going to be what? It would be V squared magnitude minus V bar squared, right? It's the second moment minus the average value squared. Do you all agree with this, class? I don't even know if he has that in the book. But it's 0.453. Yeah, he does. 0.453. And it's going to be times sigma squared. And that's sigma. I want to tell you this. This can be done by, you've got this, put 3 sigma x squared minus this, square that. You're going to get 8 over pi sigma x squared. You can just calculate that yourself. You don't have to have that. So that, I think I'm about out of time. But if we can we just take a look at, can you look at a problem with Maxwell in the back, and we'll do it. We could do the exercise. Does he have an exercise right after this one? We'll do the exercise.
He does, yeah, 2 times 6.3.
Y'all, give me a minute. We'll do it quickly. We'll do it right here. So this is exercise what?
2 times 6.3.
All right, go ahead.
In a certain gas at 400 Kelvin,
All right. Oh, I didn't get to some other, there's a few things. Y'all know what KT is? So K is the Boltzmann constant. It's equal to 1.38 times 10 to the 23rd, and that is watts seconds degree Kelvin. T will be the temperature in degrees Kelvin. And if you take a look at this, 3/2 KT is actually equal. I'm getting to the point where I'm going to miss it. I'm going to do another 5 minutes at least. Tell you what, I'm going to ask you to read that section. Y'all remember this stuff, the energy in a gas for a molecule is 3/2 KT? Do you remember Boltzmann constant at all? There was what? There was Avogadro's number back in the day, Boltzmann's constant, Planck's constant. Maybe you didn't have Planck's, but these are all like C, the velocity of light. All these things are constants from the physical world we live in, and they're directly related to either measurements for light or they have to do with statistical analysis for gases and things like this. I'll have to do this next time, okay? Now I'm going to ask you to please read these sections and do the homework I assign. I'll give you the solutions. I've got other slides, but I want to cover this. Then on Wednesday, I want to finish this chapter, and I may do one other distribution function that's useful. And then we'll get into more than one density function that are jointly related. Okay. Did y'all understand today? How many did?
Kind of so. I don't really like this.
First time I had this course, I had a great instructor. And I worked so hard. I spent probably 2-3 hours a day minimum doing the problems and stuff. It was challenging, but I was so thankful I did it. Really helped.
for the rest of the semester, we're going to be mostly working out of this book.
No, we're going back to the other one, but see, the other book's problems are more complicated. There's a lot more, they don't just expose the simple things they're trying to show. They got so much complexity. They won't have 1 or 2 things. They'll have 5 or 6 different random variables for the joint density. Well, that gets to be a mathematical nightmare to try to do in your head. So I'm trying to do it easy. Y'all understand this, guys? All right.
Square is equal to KT.
No, here, well, yes, here's what it boils down to. Here's how you get this. When you take a look at the expected value of, now this is the magnitude of the velocity, it's important, okay? That's the square root of all. That is the energy of a molecule, that's 1/2 mv squared, right?
Yes, sir.
Now look, what is this? This is 1/2, right? M times the expected value of v squared, right? What is the expected value of v squared? It's the second moment, right?
Okay.
So that's equal to what? 1/2, you'll see it, m, the expected value of v squared is what? 3 sigma squared, right?
Okay.
Isn't it, right?
Yes, sir. Yeah.
All right, so what is that? That means that's going to be 3/2 m sigma squared is equal to what? The energy, right?
Yeah.
What's the classic energy in a gas?
I have no idea.
Actually, let me find it where it's in the book. This is for a given molecule. And I'll tell you where it is. Because this is kind of classic.
I see it at the bottom of page 83.
Thanks. Let me take a look.
Is that right, page 83?
Yeah, look right above. If you go down, you're going to see 3/2 kT equal to 3/2 m, right?
Yes, sir.
So 3/2 m is times sigma squared is 3/2 kT. You see that?
Yes, sir.
That's it.
Okay.
And that means if you look at this, 3/2 cancel, right? And you get what? Sigma squared is equal to, and then you can say sigma squared. This is Gaussian sigma squared is equal to kT over m. And that's the mass of the molecule. See it?
Yes, sir.
That's it. But the problems, again, follow the same train of thought. Once you find the standard deviation related to the Gaussian, after that point, the only thing you need to do, you need the mean and the variance, but it'll be, remember, the mean is the second moment is going to be 3 sigma squared, or 3 sigma squared. The sigma is the Gaussian sigma you have to calculate. Then the mean value was, the way it was shown there, he likes to do a square root of 8 over pi sigma x. You can get the variance from there. But those are the values you need, because then if you get Maxwell-Boltzmann, I didn't get into this, but he shows you the distribution function. Where is that? This is on page 84. And I got to talk about this. But we'll do some more of that next time.
Yeah.